All right, so here's me going through example number 5 and 6 from your homework question, or from our class questions yesterday that we didn't quite get to. So if you haven't attempted them, it may be wise for you to attempt them first before examining my solutions to these problems, because the answers will be far more meaningful. So let's start out by reading through the question. So at 1,000 degrees Celsius, KEQ is 7.3 times 10 to the negative 18 for this reaction here. So one thing that I'm noticing right away is that, and I'm going to keep this in mind, I'm just going to write it up here, that this is a small value. This is a very small value. So why do we care about that? Well, it may come into as an important aspect of our question. So what does that tell me? It tells me that this reaction strongly favors my reactants, and that at the equilibrium position, when it reaches equilibrium, the relative quantities or concentrations of my H2 and O2 gases are going to be quite small relative to the amount of H2O that will be present. So this question reads, if the concentration of H2O is initially at 0.1 moles per liter, what will the concentration of H2 be when the reaction reaches equilibrium? So they're giving me an initial concentration, and they're asking me about the equilibrium concentration. So that is my cue to draw myself an icebox. So that's what I'm going to do. 2. H2O reacts to produce 2H2 plus an O2. And so my initial concentration, my change in concentration, and my equilibrium concentration are going to be what I need to consider to build this icebox. So the question tells me that I'm starting with 0.100 moles per liter of my H2O. And so they haven't told me otherwise, and so unless they tell me otherwise, I always assume that my product concentrations are 0 to begin with. And so my H2O quantity should decrease by an amount 2x, as according to the coefficients in my balanced equation. My H2 should increase by 2x, and my O2 should increase by x. So now I'm ready to write out some expressions to represent my equilibrium concentrations, so remembering that my initial plus my change will equal my equilibrium concentration. So 0.100 minus 2x is an expression for the equilibrium concentration of H2O. 0 plus 2x will give me 2x for the concentration of H2, and 0 plus x will give me an expression of x for my equilibrium concentration of O2. So this next thing I want to do is I want to write out an equilibrium law expression. So I know that in this case my KEQ is equal to the concentration of my products, H2 and O2, and the exponents in this expression are there because my coefficients in the balanced chemical equation. So in other words, I see this 2 here beside H2, that brings me to have a 2 here in my equilibrium expression. All of that divided by the concentration of my reactants raised to the power of their coefficient in the balanced chemical equation. So there we are. But I know K. I know the K value is 7.3 times 10 to the negative 18. So I'm going to substitute that in. I also have some expressions for each of my products and reactants present at equilibrium. So I have 2x all squared and then times x divided by 0.100 minus 2x all squared. Let me create another little column here. And what I'm going to do next is I'm going to see if I can simplify this. So let's take a look at this. So we'd have 7.3 times 10 to the negative 18. And so this is one thing worth mentioning. Often people, this is a mistake I see often, when people are squaring 2x all squared, sometimes they will write 2x squared. But remember, this 2, this exponent of 2 applies to the base 2 as well. So 2x all squared gives me 4x squared. and then multiplied by another factor of x will give me 4x cubed. And I'm going to divide that by my 0.100 minus 2x. That is an x, people. It's all squared. All right, so here's where chemistry and math deviate, and we're going to have to do some practical stuff here in estimating. I don't know about you, but I am not in the mood to solve a cubic function, so instead I'm going to do a little bit of reasoning. So remember at the beginning of this question, we talked about how the amounts of H2 and O2 would be really small at equilibrium because as indicated by my small KQ value. So what that means for me in real terms is that the value of x and 2x, those will be extremely small amounts. So in other words, this little amount here, 2x, that is being subtracted from my initial concentration of H2O, 0.100, is going to be really, really, really small. Let's just do an exercise just for the sake of doing the exercise. If I have 0.100 and I subtract something that's in relative terms quite small, so I'm going to say, let's say like 1.0 times 10 to the negative 10, oops, negative 10. So then I try to type that into my calculator. Chances are you're essentially going to end up with 0.100. The difference is going to be so small that your calculator doesn't even register it. So in essence, the amount is negligible. And so if it's negligible for all intents and practical purposes, then what we can do mathematically is just kind of get rid of it. It's not going to make much difference anyway. Let's just get rid of it. And that's where that estimation comes in. So here's the lesson, when KEQ is quite small relative to the initial concentration of our reactants, then the value of our equilibrium concentration of products is really, really small, and sometimes that means we can simplify the math. So 4x cubed, now I can rewrite this as 0.100 minus, 0.100 all squared, and that's a lot easier to solve. So now I'm going to bring this expression up and essentially then solve for my x value here. So that will give me 7.3 times 10 to the negative 18 times 0.100 all squared, and that's going to be equal to 4x cubed. So now I'm going to divide out the 4 before I cube root it, because that will just make my life a lot easier. And so then once I've done that, my 4's will cancel. And then you got it. I've got to undo this cubed roots, this cube, so I'm going to cube root what's on the right, and whatever I do to one side, I need to make sure I do to the other side of this equation. And so then that allows me to solve for x. And when I type those values correctly into my calculator, and I'm going to put this to 2 significant digits based on my the values I've used, I'm getting 2.6 times 10 to the power of negative 7. And remember, that's a concentration. That's what x is representing, so I'm going to use the big M to mean moles per liter. Now remember, the question initially was asking me for the concentration of H2 at equilibrium. So the concentration of H2, you'll remember, was given by the expression over here, 2x. So I need to double that value in order to answer the question fully. And that will give me 5.3 times 10 to the power of negative 7 moles per liter. And so now let's think back about, some of the choices we made when solving this. We said, well, this amount 2x is going to be hardly anything. It's going to be so small, it's not even going to matter. And so at the end of any question where I make those decisions, when I make that assumption, I need to go back and evaluate my answer to see if that was a fair thing to do. So in fact, when I look at the value that I get for the equilibrium concentration of H2, I see that it indeed is quite small relative to the initial concentration of H2O. And so that was a valid assumption to have made, and my solution stands. Let's take a look at this at a second question. So this is example 6. So in this case, it seems they're giving me a KEQ value, and they're asking me to solve for equilibrium concentrations of both my reactant here and oh no, only my reactant appears. Okay. But they're giving me an initial amount. So that's my cue to write out an ice box. So I'm going to go ahead and do that. So N2O4 reacts to make 2NO2, and that is balanced. Always good to double check. So they're telling me that I have 0.50 moles in 1 liter, so that tells me my concentration. And as always, I'm going to assume that anything that I'm putting in my ice box is in units of moles per liter. And they haven't told me otherwise, and so I'm going to assume that I have 0 moles per liter of NO2 at the beginning. So my N2O4 is going to decrease by an amount x, and my NO2 is going to increase by an amount 2x. And so that gives me some expression, 0.50 minus x and 2x, respectively. All right, let me carry on with this solution. So the next thing to do is to write out my equilibrium expression, KEQ. So KEQ for this will be the concentration of my product NO2 all squared divided by the concentration of my reactant N2O4. And I'm going to encourage you not to skip this step, because I've seen many students make mistakes by cutting corners, by skipping steps. So my KEQ value for this is 4.50, and it's worth taking a minute to just think about that. That is not a very small value, so that it means that I can't really get rid of any expressions in my equilibrium law, because it's really not going to be valid to do that, since there will be a fair amount of product present at equilibrium. So let's go ahead and sub in what I know. So NO2 is 2x all squared divided by 0.50 minus x. All right, let me create another column here and carry on. So I'm going to simplify this further. 4.50 is equal to 2x all squared divided by 0.50 minus x. Now, as I said before, this is a case where I can't get rid of this x. So what does that mean for us? Arg. That means I'm going to be stuck with a quadratic function, and that will mean using the quadratic formula. So in order to do that, I need to rearrange this formula in the form, I'm going to write it up here just to remind you, ax squared plus bx plus c equals 0. So in other words, I need to take this expression and rewrite it in a form where I have the whole one side equal to 0, and that will allow me to have my a, my b, and my c values to use in the quadratic equation. I'm going to go ahead and do that now. So 4.50 times, and that's just me bringing this expression upstairs, 0.50 minus x is equal to 2x all squared is 4x squared. I'm going to simplify this. So I'm actually just going to write my 0 over here, because I just like to have my x squared value positive. So 4x squared. Now in the meantime, I'm going to have distributed both of these values so that I can multiply them and then move them to the opposite side of the equation. So half of 4.50 will give me 2.25, but I'm going to move that to the opposite side of the equation. Oops. and that will give me negative 2.25. And so then I have negative 4.50x, but I'm going to move that to the opposite side of the equation, so 4.50x will be positive. I'm going to rewrite that in order of ABC. So 4x squared plus 4.50x minus 2.25. So what I'm going to do at this point is a little bit of magic. I'm going to let you go ahead and solve your quadratic equation using the quadratic formula. And I'm simply going to plug the values into a quadratic equation solver. So with any quadratic equation solver, you end up with two roots, right? It's a quadratic, so you'll have 2 points of intersection with the x-axis if you were to plot this as a function. So the two answers are x is equal to 0.375, and this is moles per liter, and x is equal to negative 1.5 moles per liter. Now we know, of course, that, in this case, in the context of the question, this solution right here does not make any sense, so we're going to ignore it. Right here, our 0.375 moles per liter is the value of x for this equation. Now remember that my original question, really, I haven't answered it yet. The question that was initially posed to me was, what is the equilibrium concentration of my reactant? And so I need to go back, and I'm going to, just to save space, I'm going to go up here and I'm going to solve for that. So 0.50 minus 0.375. And once I perform that difference, the concentration of my N2O4 will be 0.125 moles per liter. So now I'm just going to also take a minute to look at the reasonableness of my answer, just to make sure it makes sense. I have a K value that is a little bit over 4. So that means that the relative amounts of my products and reactants are going to be, similar. And so really they're on the same scale, right? So the amount of NO2 is going to be 2x, so 2 times 0.375, and the amount of N2O4 that I have is 0.125. Those are on the same scale, which is reasonable for this answer, and my reaction is slightly shifted towards my products. So that is a valid solution. So now what your job is to try to make sense of these two questions and practice using the worksheet that I provided on Google Classroom for you. If you have any questions, please be sure to save them for Monday and I'll be happy to answer them.